Yet. You see the recording button? There is a recording button, if anybody can confirm.
Yes.
Okay. Okay, thank you so much. So, my name is Mazen Hilali. I'm a senior petrophysicist working right now with local Mid East in West Gorna Phase 2 project, southern Iraq in Basra. We will this is a part of series of webinar focused on production logging. This webinar will be presented by Mr. Alain Gysen. I will make just 2-3 slide presentation before Alain start, and I will keep the mic for Dr. Mohammed if you want to introduce himself and welcome with the attendees. Dr. Mohammed. Okay. So I believe you have some technical issue. Okay, so I will share my screen. I believe my screen. You can confirm my screen shared?
Yes.
Okay. So I like to welcome our lecturer, Mr. Alain Gysen, and this webinar will be in part of the year 2024 theme focus on production logging. The webinar subject is production logging analysis utilizing PLATO software. Sorry, a mistake, not by Kappa, by ISP company. Okay, I will correct this because it will be ISP company. We did quite some webinar this year. This is our 8th webinar. All of them is focused on production logging from manufacturer side and from software side. Mostly we'll have 1 or 2 webinar this year. Okay, and I like to thank all our sponsors and tutor which dedicated their time to volunteering for SPWLA activities. We'll provide a special certificate for the people who attend of 6 or more webinar, and will be our pleasure if you can join our Iraq chapter for SPWLA. Just small housekeeping. Okay, it's if have any question, okay, you can write it in the chat box. Okay, and if you like to talk, you can keep it at the end of lecture. Okay, and a small introduction for Mr. Alain Gysen. He's expert in PLATO software. I believe we can say it is the geoscience manager or geoscience domain. Okay, well, I can't keep the introduction for yourself, Alain. Okay, and before that, like I'll just keep the mic for Dr. Mohammed if you want to. Okay, add something.
Yes, thank you, Mr. Mazen. Hello, everyone. Today is the 14th of October, 2024. We at SPWLA Iraq chapter are pleased to welcome you and to have you join us today. My name is Muhammad Jawad Zainul Abedin, VP of Technology at SPWLA Iraq chapter and Senior Faculty Member at Petroleum Engineering Department, College of Engineering, University of Kirkuk. The 8th webinar in 2024, Production Logging Analysis, utilizing PLATO software of ISP, will be presented by our speaker, Mr. Alain Gysen. Welcome to you again, Mr. Alain Gysen. During the presentation, we will send a link in the chat box to join the SPWLA Iraq chapter on LinkedIn. Thank you.
Thank you, Doctor. Okay, the mic for you, Alain. You can start share your screen.
Okay. Can you see my screen or?
Yes.
Oh, yes.
Crystal clear.
Okay, so I'm Alain Gysen. I work for ISP. ISP is Interpretive Software Products. We are most well known for the software PLATO. PLATO is PLATO is the production logs analysis tool. And so I've been working for ISP for over 20 years. I do interpretations of all types of PLT data, DTS data, and DAS data. I also provide the trainings to customers and customer support if needed. Yes, I can go to the next slide. So the main office of ISP, where our CEO is based and where we have our development team, that's in Houston, Texas. I am based in Belgium, and one other of my colleagues that does marketing and sales, Diane, who is not there today, but she is based in France. So ISP, we have been on the market for over 30 years, mostly in the domain of production logging, but also we have put a lot of emphasis on distributed fiber optics interpretation. So we were very at the early beginnings of fiber optics, we were involved. Therefore, our software is can handle fiber optical data very well. Let's go to the next slide. Our software is used in a number of several continents. In the United States, our software is used in South America, in Europe, also in the Middle East. We have customers in the Middle East, in Iraq specifically, also in North Africa, in China, we have a lot of customers, and also in the Brunei area, our software is used. This slide is a little bit more like a corporate. So what we provide is we provide software solutions. So we sell our software, but also we provide consulting services using our own software. And for customers that bought our software or are leasing our software, we provide custom trainings. So we could do trainings with the typical training data sets that we have and our own schedule. But very often customers ask to customize training to use their own data, and that is very much possible. Yes, so here, this is a new slide, so I have to get used to it a little bit. So yes, over 30 plus years, we are operative in 5 continents. We have some major operators that are using our software, and some of these operators and also some of the logging companies are using PLATO as their corporate production logging package. And PLATO, it's used because it's very stable and because it's very accurate. And next slides are showing which type of software packages that we provide as ISP. For production logging, we have PLATO PLT, and PLATO array tools. So our philosophy is to sell the different modules separately, because we have many customers that only do conventional PLTs and they would never do an array tool analysis. So making them pay for an array tool module it's not making sense. Also, you will see here we have different packages for fiber optics. These are also modules of PLATO. Somebody that is never going to do a conventional PLT, only DTS, we are not going to force that person or that company to buy the PLT module. Of course, it's possible to have all the modules, or we can provide uneven fleets. For example, that our customer has a network license with 5 licenses for regular PLT and 1 license for DTS and 1 license for array tools. So we are very flexible in that for that part. So let me go one step back. So for production logging, PLATO production logging analysis, this includes the temperature model, the optimization. The PLT, conventional PLT is for centralized PLT tools. So all of the vendors the tools for all of the vendors are implemented for the Schlumberger tools, Baker Hughes tools. And array tools, array PLT, we are currently compatible with FSI data, MAPS data, by AccuPhase for FAST. For FAST, we have several services to make it easier to interpret fast data, to allow combinations of their V2 and V2 and V4, their slim fast. So we can, for fast, we have done a lot of work to be very compatible with their tools to allow different combination of tools. And then just we are currently adding more tools from other vendors, but this is for the array tools. Then for fiber optics, there is PLATO DTS. PLATO DTS is also a package that allows to calculate production profiles using distributed temperature sensing data. So this is a complete module to handle fiber optical data. We have models for Warmack analysis, that is analysis where you try to infer the injection profile from shedding data after the injection. These models can also, we have also specific models for hydraulic fracturing, both for Warmack and for flowing wells. And then for DAS, DAS for a long time has been a separate package, more like a visualizer, so that DAS data can be visualized together with DTS data. But now this DAS module, it has been integrated in PLATO. And so I will talk a little bit more about that in a little while. And then another software package is SP2S. This is something that falls outside of PLATO. SP2S is a software that we created to do pre-processing of DAS data, because DAS data is typically of a very large size. You have several terabytes of data, and this is not data that you can easily share over the web or share amongst each other or your colleagues. It's not practical to work with several terabytes of data. So what SP2S does, is pre-processing the data, normalizing the data, filtering the data, but most importantly, it's decimating the data into ASCII files, with one ASCII file that contains the frequency band energy for one timestamp each. And on these last files, you will see we contain the DAS energy for up to 21 frequency bands. So this is a preprocessor for DAS data to reduce the size from terabytes to gigabytes. And then we have another package, Resolver, that's for formation evaluation. And yes, this is not the package that is the most popular amongst our customers. Most customers are using PLATO. And as you saw here appearing when I clicked on the button, in PLATO 8, we are integrating all the PLT, DTS, and DAS in the same analysis package. So if you have DAS, DTS, and PLT data acquired for the same well, you can import everything in the same project and analyze all the data sets within the same project. So it's in fact, you integrate all the information you can obtain from various sources until you have your final result, and then you can confirm that your results are accurate because you have all these sources of data. Yes, so all of our flow allocation programs, that's PLATO DTS, PLATO array tools, and PLATO conventional tools, they're based on a probabilistic principle. So what we do is we optimize a well model by using a probabilistic technique. So the probabilistic technique works as such that you have a model of the well, and this model of the well allows to generate theoretical curves. In this particular case, you have a theoretical density, a theoretical capacitance, a theoretical velocity, temperature, pressure gradient, and these theoretical curves are compared to the actual data. And comparing the measured data and the theoretical data allows to generate an incoherence curve, or just an incoherence function, in fact, which is, we use the chi-square error function. You can see the function right here. It's a published incoherence function. It is summation over all the tools and all the samples of the squared difference between the theoretical measurement and the actual data, divided by the uncertainty on the measurement to the power of 2, so the squared uncertainty on the measurement, and this is this uncertainty, it's calculating during pre-processing subtask in PLATO. So what we do is we are optimizing a well model by minimizing the incoherence between the model and the data. And you will see that on the next slide. The next slide, it is showing the result of such a PLATO analysis where convergence has been reached between the data and the model. The model, it consists of the holdup, the flow rate, and the flow regime. And from this model, the holdup, flow regime, and the flow rates, PLATO can generate theoretical curves. So for all the data that has been acquired, a theoretical curve is generated, and the curve is shown in red, and the data is shown in blue. So this is velocity. You can see a perfect match for the apparent velocity here. Then there is pressure gradient. It's not so great, but it's still matching. Then we can add the temperature because it's a probabilistic approach. It's optimization of a probabilistic model. So we can add any amount of tools as long as there is data acquired for this tool. So velocity can be combined with temperature. We can also add the temperature, the gradiometric density, the electrical conductance holdup for water, so the depth in this case, and we can also add local constraints for the average stationary spinner RPS value. So these are local constraints on the stationary spinner, and you select as a user the time interval over which you want to average, so that you can skip any kind of slugging. So in this optimization, we used pressure gradient, gradiometric density, conductance, and for spinner data we could use all the continuous data and stationary spinner averages. And as an additional constraint, we added the temperature, and the reason for that is that we observe this frictional heating effect here that is marking the first fluid entry, and this is not this temperature change at this depth. The spinner is not showing an inflow, maybe because there is a little bit of water recirculation there, or because the volume is not large enough, but the temperature shows that there is a little bit of production coming from below where the spinners are starting to pick up flow. So you can see here an advantage of this probabilistic approach is that you can have a model that is in agreement with all of the data. You don't have to throw away data because you, for example, if you have two-phase analysis, you only can use one tool, or three-phase analysis, you can only use two holdup tools. We can use all the tools in a model. Then, of course, not all the data will be of the same quality, and maybe there will be zones where a particular tool failed. Therefore, we are slightly modifying this incoherence function by introducing a weight multiplier, M. So for each measurement, there is a weight multiplier, and this will influence the weight of this particular measurement on the optimization. It will be very clear on the next slide. On the next slide, this is an interesting case where PLT data was acquired in a deviated well, and there was one section where there was a significant water recirculation. You can see here the velocity, it's increasing at every production zone, also here, but here you can see there is negative flow. Also, the density is suddenly showing a higher water content. The density is increasing, and the capacitance, this is a capacitance that's measured in 1/RC. It's the classical capacitance tool is also showing the presence of water. So this is a section where you have two packers here, and production is occurring along the pre-drilled liner, which is in between the two packers. And our customer, they would very much would have, back then, they wanted very much to be able to quantify the production from the different sands between the two packers. And with the spinner data, because of the recirculation, this is not possible. The spinner data is only showing water recirculation, and there is no information provided on the hydrocarbons that are moving up at the higher side of the well. So if you would have had array data that completely covers the production casing, then you would have enough data to quantify the amount of hydrocarbon moving up at the higher side. But in this particular case, you don't have this. So what we tried in this dataset is to reduce the weight on all the conventional tools in their water recirculation zones and activate the temperature constraint in this recirculation zone. And in this, I'm not saying that this is the solution for every time that you have this water recirculation, but in this case, it's worked very well. So we modeled the temperature. The temperature is showing a clear temperature decrease here. If we would blow up the scale a little bit or change the scale a little bit, we would observe some temperature changes here. And these production rates here have been calculated from the temperature data and not from the spinner data and the other data on which we reduce the weight multiplier. So this is, so for every tool, if the data is not good, you can reduce the weight. If the data is not reliable for across the entire interval, you can just remove it from the optimization. Then a few slides that are highlighting the benefits of the approach. So the first, yes, it's a global three-phase model. So flow rates are optimized by minimizing the incoherence between theoretical and measured tool responses. That's what you see here. So the optimization tries to get a match between the theoretical curves in red and the measured data in blue. There is this color-coded incoherence here. You can see that there is material balance, slip, tools, and temperature incoherence. So if there is an incoherence between the model and the data, you will see for which type of quantity this incoherence is occurring. If it's tools, that means that there is somewhere a tool match the theoretical and the measured curve for a tool is not matching properly. If it's material balance, that means material balance is broken somewhere. That means that somewhere you may have a decrease in flow rate, which cannot be explained. It may be the data that's showing it, but it's maybe a data issue. And therefore, if you want to enforce material balance, if you don't want material balance to be broken, then you can tighten the material balance constraints. So these are incoherences, and they provide for all these incoherences, there are constraints to really handle those incoherences. So yes, material balance can be constrained because we are using mass rates internally instead of volume rates. There is versatility because we can use any combination of selected tools, including temperature and stationary data. And these weight multipliers, they can be zones. Here as well, you can see it's a very interesting case. The temperature is clearly showing some frictional heating here. But the temperature, it was showing the velocity was showing recirculation. So the velocity was only showing recirculation, while the temperature is really showing this frictional heating here. So what we could do here is reduce the weight on the velocity and increase the weight on the temperature and make sure that our temperature model is accurate to really model these frictional heating events correctly. So we have a result now that's based on the velocity in the zones above the water recirculation interval, but across the water recirculation interval, we are relying more on the temperature. Then for the spinner processing, we are also using more of a probabilistic approach, and that means that we are calibrating the slope and the threshold and the velocity by generating theoretical curves for each spinner pass. So for each spinner pass, a theoretical curve is calculated, and the RPS curve is calculated using the slope, the threshold, and the theoretical apparent velocity. And you will see when we do the example that the program also minimizes this incoherence. You have the incoherence track. So the apparent velocity and the slope and threshold that is obtained is in agreement with all the data. Of course, with spinner data, you have many cases where spinner data, in some intervals, the spinner data is of poor quality, some passes fail completely. So we have quality flags parameters so that you can manually remove the bad spinner data so that you obtain an apparent velocity curve that's in agreement with all the data, and you remove the data that is not reliable. So here is a result of such an optimization. We have a good match between theoretical and measured curves. We are not using linear regression, but to make this a little bit more intuitive, we are also adding station plots, a particular depth where we show the spinner data versus cable speed and also the linear fit. And this additional curve, this is the final QC curve that is showing the RPS data versus the relative speed between the fluid and the cable. That means that this is a shifting of some kind of shift we apply to the static response. So the spinner analysis in PLATO is a separate subtask that takes a lot of time, but the advantage of this is that you have direct QC of whether a curve can be used for the spinner processing. If it's not of good quality, you can remove it from the analysis manually. Even on this plot, if there is a blob of bad data, you draw a box around it and it's not used. So using this approach, we don't need a static section to calibrate the threshold, and we can also provide spinner polarity corrections. If the data is acquired in the wrong polarity, the spinner is all positive, just in absolute velocities, or the line speeds are in incorrect polarity. All of these issues can be amended for. Then the depth matching, of course, every software package does depth matching. I suppose every PLT software package provides depth matching. We use depth matching using depth anchors. And when depth matching is performed, a new set of curves with a dash core suffix is created. So that means that the raw data is not overwritten. You still keep the raw data in the database, but a new set of curves with a dash core suffix is created, and those will be the curves that are going to be used in the rest of the analysis. But once these dash curve depth corrected curves have been generated, you can still go back and apply more or less depth shifting. If you realize, okay, this curve, I forgot to depth shift it, or I did too much depth shifting, let's reduce it. You can always go back and redo the depth matching. Then for temperature analysis, yes, we have a model based on the enthalpy balance in the well and the reservoir. This model includes Joule-Thomson behavior. The temperature model can be combined with all other tools, including spinner data. and the flow rates, if the flow rates are optimized by minimizing the incoherence between the theoretical and the measured temperature. What you see here, this is data acquired in a horizontal fractured well, tight gas, and you can clearly see that there is Joule-Thomson cooling at every fluid entry. The red curve is the theoretical temperature, the blue curve is the measured temperature. So the profile here has been obtained by optimizing the temperature model, and doing so we optimize the production profile. So we have a very good match for our temperature between the measured and theoretical temperature. Okay, so the temperature model, it's a very complete model. We do different types of, we have different possibilities for geothermal. All the parameters that have an effect on the temperature are included in the model. Then some few examples of to show the versatility of this probabilistic approach. You can have here, this is a gas and oil producer. Schlumberger tools, you can see we are using velocity, pressure gradient, the gradient density, the depth, the ghost, and some stationary measurements. So here we are using all the acquired hold-up data for the optimization of the well model. And for the spinners, we include the continuous spinner data, but also the local stationary averages of the spinner data. Then another example, this is a vertical well. It's also fractured wells. And in these fractured wells, there was a lot of slugging occurring. You can see here this temperature data, the velocity data is not of the greatest quality. In the tool string, there was a gradient and of course pressure. But what we noticed is that the temperature is a lot more sensitive here in these cases. All of the slugging makes it impossible to really identify or to quantify how much is being produced from one perforation. But the temperature gradients here, this track, it's spiking at every fluid entry. So for this customer, we helped them to build the template or the processing approach for this type of data. And this was an approach that included also the temperature and the Joule-Thomson cooling resulting from the gas production. So here, after this customer implemented PLATO, they finally had a good handling also of the water entries, because the water entries were very, very small. And once they added temperature to the model, they got the proper allocation of the water production. Then, yes, you can use a limited data set, just velocity, pressure gradient, and gradient. Here, everything is showing a single phase gas, and the spinner data, or the apparent velocity at least, is showing cross flow during shut-in. So fluids are being produced in the upper sands, they are flowing down and then injected in the lower sands. So this is cross flow in a 40% deviation well. And then final example here, it is a well where there was 49% water cut. The well was 20 degrees deviated. And we used the gradient manometer, the conductance, that's the depth, and then the spinner data. And we could establish the oil flow rate where oil was entering. Okay, so this is all for PLT. I will quickly go over the other software we have because we only have one session now. So for PLATO array tools, we use the same approach for PLATO array tools. So with the calibration of the array tools, with that we mean calculating the layered profiles, so layered velocity profile, as you can see here, the layered holder profile, as you see here. And these layered profiles, they are calculated and calibrated, especially for the spinners or for other tools that need the calibration, by using this probabilistic approach. So we are generating theoretical curves for each pass for each sensor, and we are PLATO is minimizing the incoherence between both. So of course this is a lot. It involves a lot of more work than conventional tools. You have to look at all of these different array tools. As you are aware, there are currently some collocated tools that are very flexible so that you can use different combinations of probes, but therefore the PLATO has to be very versatile, but also you have so much more data that you have to look at. So you have to look at every probe. You have to check for every pass for every probe whether you can use it for the processing. This is a simple case. Well, a simple case. In fact, a bit of an old data set. It's MAPS data in 70% deviation well. And so we have the SAT data, the spinor data, and the RAT, the resistance array data. And these layered velocities, you can see hydrocarbons moving up here at the higher side to this higher velocity here, hydrocarbons moving up here. Is what is calculated. When I talked about the spiral processing in PLATO, we are not using linear regression, but we are optimizing a velocity model by comparing theoretical curves and measured curves. Therefore, also if the tools are rotating for array tools, we can still generate a theoretical curve because we know the position of the tool, we know the relative bearing. So for each tool, even though the tools are rotating, we can estimate the theoretical response. And here you can very nicely see these tools are constant. This tool string is continuously rotating, but the PLATO is taking account of this rotation and it's perfectly matching these rotations, both for the spinor and the RAT. Then there is a very nice data set for FSI. This is a truly horizontal well, and here you can see the layered velocity, and the layered velocity is in a great agreement with the inclination. So the blue shading are zones where the inclination is above 90. The red shading is when the inclination is below 90. So below 90, you will see water recirculation, so highly negative speed at the lower side of the well. But if the inclination gets higher than 90, the trajectory goes down, sorry, and then water will start moving fast. And that's what you are seeing here. So the inclination is changing, trajectory goes down, and water is moving fast. So this data set is very good. You can see the changes in velocity according to the changes in well inclination. So here again, it's a trajectory going up. The deviation is below 90. You can see a highly negative velocity, and the hold-up data is in perfect agreement. So in the recirculation zones, the water hold-up is very high. Then where in the zones where the water is moving fast at the lower side of the well, the water hold-up is decreasing. So this is FSI data sets of good quality. Then we have some fast data, also very good quality. You can see some spinor data here. It is showing hydrocarbon moving up at the high side of the well, and the other spinors are showing water recirculation. And all of the hold-up tools are confirming the same scenario. So you have water at the low side of the well, hydrocarbon moving up at the higher side of the well. So yes, so for all the interpretations we do for array tools, in fact, we are using the same model. We don't have to use another model for a different tool. So for us, an array tool is just a tool that we use to update our layered models. If we have, therefore, we are capable of implementing new tools very quickly because, in fact, what the tools do is provide us information to optimize the models. We don't have to change the model depending on the tool type, which of course you have to implement the tool type, the relative positions between the probes and the technology. but the profiles are optimized. The profile optimization is done by using the acquired data. Okay, then how much time do I have? Okay, still, okay, so maybe I should go to the PLATO projects now. So PLATO DTS, we have all the different visualization types, color, curves, color maps. We have animation mode. You can look at the temperature versus time at particular depths, wavelet visualization, and also for PLATO DTS, we can obtain results with the temperature, and if pressure data is available, of course, it helps to differentiate in between phases. For DTS, this is exclusive to DTS. It's the Warmback model. The Warmback model, we have a model for fractals. So to analyze the Warmback data, the flowback data after fracking, but also for open hole laterals, we can analyze the Warmback data. So we have two models for Warmback analysis for DTS data. For fractals and horizontal laterals. And what we do is PLATO is generating theoretical temperature history, shut-in traces, and by these shut-in traces, they are generated from the injection profile. So by minimizing the incoherence between the shut-in history, measured and theoretic, we optimize the injection profile. Okay, so I think I have to speed up a little bit. Yes, then just for the DAS, what we do for DAS. So typically the raw data for DAS, it's in the terabytes. One job may consist of a box of 5 hard drives that are completely full. And of course, that's not very practical to use to work with. So our first in the workflow is SP2S, is the pre-processing software. And the pre-processing software, it is kind of decimating the data so that you have one file per timestamp. So when SP2S is running on your raw database, raw data, these files, these are ASCII files with the timestamp in the file name are generated, and each of these files, sorry, they contain the timestamp, so time and date, and the DAS energy for 21 frequency bands. And these are frequency bands that the user can change. So you would select frequency bands where you expect fluid movement to occur, or if you have another purpose, you would select frequency bands where your event would be visible. Then this data, the decimated data can be imported into PLATO DAS, and then it can be visualized together with DTS data. For the visualization, we can see here, we are currently displaying 6 frequency bands. And the frequency bands, they can be synchronized if we do a zoom, a time zoom, or a depth zoom. So these are functionalities in PLATO DTS, PLATO DAS. So yes, if I will repeat it here, these diagonal lines, they show fluid movement. You can see them typically in the lower frequency bands. In the higher frequency bands, you may see completion items making noise when the choke settings are changed or when injection is occurring or production. Then we can do time synchronization of DTS and DAS data. Here you can see the DTS data during a fracking job and the DAS data also during a fracking job, and they are time synchronized. So you can see at what depth and what time a particular event is occurring. So this is all for fiber optics. And then before I start the example, for our new release, PLATO 8, that is coming out this month, we have included some processing of the DAS to help to assist with the production log analysis or the flow allocation. Let's first look at the slide on the left. This is a screenshot of a conventional PLT data set. You have temperature, your temperature gradient, the derivative of the temperature is nicely showing where production is occurring. Also, your velocity is really increasing where production is occurring. So here you can label zones as potential production zones very easily by looking at the data. And of course, you have the perforations. But we have faced a lot of interpretation. We have received a lot of interpretations of multi-stage fract wells, and these are wells with at least 24 stages with 6 perforation clusters per stage. Once we had with 100 stages. So, and then if you look at the temperature is very noisy, so it's hard to define whether this temperature change that you are observing is actually just noise or it's actually an inflow. And if you look at the DAS data is showing those horizontal lines, and those horizontal lines only appear during flow because this data is acquired during shut-in, flow, and then a shut-in, and these horizontal lines only appear during flow. Therefore, they are indicative of fluid entry, and their intensity will show whether more or less production is occurring. This is a color map, so that shows that the intensity over a time sequence. This is a more of a curve visualization. It is showing different DAS traces in the energy scale, where this is a color map. But here it's much more different. You are not able to select zones manually here. So what we have implemented is some kind of a automation to extract potential production zones from the DAS data. So these production zones here, where the DAS is showing a high intensity, they can automatically be detected from using our algorithm. And then, yes, this is the last slide before the project. So what we do is for different frequency bands, we calculate the total DAS energy over a time where there is steady state flow, and then we can specify thresholds. So a threshold to determine whether a particular energy corresponds to production or not, and we can put 2 thresholds, one for high production and one for lower production, and eventually, when we want to do some more automation to label zones as potential production zones, we can now include the temperature gradient, the profile from the DAS, and the perforations. So you have this dialog now where you can specify the sources, manual input, or perforations, DAS intensity, pressure, temperature gradient, and you can make it so that those zones, production zones, are only selected if a production is shown by every measurement, by the DAS, the temperature gradient, and also it has to be a perforated interval. So this is to improve automation. Of course, a lot of interpretation still must be done by the analysts that is to be carefully specifying production profiles, production zones. Okay, so those were a lot of slides. Let me go to the PLATO workflow. The PLATO workflow for standard PLT consists of 6 steps. First, data import and QC, pre-processing, spinner calibration, profile building, and optimization process, and eventually calculating the surface rates from the optimized downhole production profile. Let me go to the first subtask, or this first step. In fact, it is reviewing the data. So reviewing the data, I will open PLATO to show you how it's done. But reviewing the data is typically making sure that all the important data can be accessed and visualized. what you can do is you can change the processed interval. Typically, you have some poor data above the logged interval or below. So you reduce the interval to the interval where you have good data. You can specify some completion items, perforations in this case, perform depth matching if needed. And yes, let me go with create the PLATO project. So the current approach to generate a PLATO project is you create a project like this. This is opens a window. In this window, you type the project name. So I can call this webinar or SPW, webinar September 2024. Then the analyst name, it's my name. Of course, if you install PLATO, it will be your name. You press next, then project path. I'm not going to spend too much time on that. That is where you are saving the files for the project. So we have these three little dots here. If you click on this, you can specify the folder where you want to save the PLATO project files. Then there is import files. So you generate the PLATO project using the imported data, typically LAS data. And to import data, you click here on this little plus. And then you can browse through your files and select the data you want to use. For this analysis, I will see how much time I have, but I will start with the flowing data. So this is a file that is containing all of the passes for this job, flowing data.las. I will keep the API unit system. I will select metric in a different window. You can see that there is this option here. There's an option that we have implemented for Shell, because Shell, as you know, it is using gas, red for oil and green for gas in some locations. And then the Shell analyst or the analyst that is performing an interpretation for Shell has to check this box, of course. Okay, so I selected the files I want to import. I go to next. Here you can change the well step if you want, but this is the well step that has been found from the data, which is half a foot. The well range, that's the maximal value, depth value, the minimal value, depth value, then the maximal value on the found on the last files. You can enter a depth shift, that is a depth shift, a block shift, to shift all the data up or all the data down. It is not the individual depth shifting that you do for pass per pass. So this is a block shift. And in this particular case, it's not required to do a block shift. You can press next. And here you specify the module. This is not PLATO 8, so here it's one module at a time, but PLATO 8 that will be released this month. You can select a combination of modules, PLT, DAS, DTS. In our case, it's a PLT. For PLT, we have a list of services, and these are, in fact, the names of the logging company and the particular tool suite that they are offering. So you can see here, PLT, we have the different vendors, including Schlumberger PSP for Schlumberger Flagship. Then if you look at array data, the services are Baker Hughes Array PL, Baker Hughes Maps, OpenField. We have different entries for, or different options for OpenField Fast. The spaghetti is actually SlimFast, but also V2, 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 V4, 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 and the Schlumberger FSI. And selecting a service, what selecting a service does, it is automatically presetting the log names. So for each channel, the correct log name is set. Also, it loads the correct tools. Here, if you look at fast V2, V4, it's making sure that the first tool is the V4 and the second tool is the V2, so that the correct channels are provided. The necessary channels for each possible tool are provided for the V4 tool, and then for the V2.
Sorry, Elodie, I think we can hear you. Sorry.
Yes,
Right.
yes.
Sorry, you wanted to ask a question to Alain? Everybody can hear you. Sorry, no. Alain?
Yes?
Yeah, I think you can go ahead. I have another question. It's great that you speak about the different type of tool of OpenField, but I keep my question at the end if we have time. Thank you.
Okay, so it's mostly to preset log names and also to set the correct channels so that the analyst just has to import the data and doesn't have to worry about is this sensor data mapped to the correct channel. Okay, but here we are going to do a very simple case. So service is Schlumberger PSP. The data set, it is gas, oil, and water. Press next. You always get a summary of the data you're importing, the project name. Okay, so I see here that I should go back and select metric depth units, because this is an asset that uses metric depth units but prefers barrels per day and degrees Fahrenheit for temperature. So they prefer only depth, metric for depth, but API units for other measurements. So Schlumberger PSP production, gas, oil, and water. And that's what we also see in the summary. So then you create a project, and let me move it here. So a PLATO project is then created containing all of these data. You can see PLATO is working with a ribbon structure. You have a home tab. The home tab, it contains all the buttons required to do most interpretations. So you have the sampling button, all the computation buttons, zooming options, also the workflow, where that I mentioned briefly, data QC, pre-processing, spirit calibration, profile, process, and post-process. So the workflow is shown here. And then there are some shortcuts to specific screens or editors. Then, of course, you have Edit tab, View tab. In the View tab, of course, there are zooming options, but you can also, for example, if you are more accustomed to dark backgrounds, you just click dark backgrounds, and then the backgrounds are black if you prefer black backgrounds. It's very easy to do. You can hide up and down passes. So this is a ribbon structure that is that we are using very much like any other software, I assume. Then there is the browser tree, and in the browser tree, you can see which image is currently visualized, and also for this image, which tracks are currently visible. We can see here there is no ghost data, so we can hide the ghost data. So if we uncheck ghost, it's disappeared. So the gamma ray, yes, there is gamma ray, but no azimuth data, so we can hide the azimuth data. So this is you can use this to hide specific tracks that you are not going to use, or to bring them back. What you will notice is that the scales are not appropriate for this tool set yet. The scales are too wide so that you cannot really see the data well. Therefore, we have like an automatic scaling implemented. It's called rescale. If you click the rescale button, all the minimal and the maximum scales are set appropriately to the minimal value on the data and a maximal value on the data. And now you can see we have temperature, pressure, gradient, the depth water holdup, the line speed, spinner, gamma ray, CCL should be there. We have inclination and caliper data. Then what I'm going to do is I'm going to check if there is not CCL data imported that we just don't see it. To do that, you go to an editor, and in this editor, the global editor, it opens in the input data group, and it gives you access to all the mapping parameters. So for temperature, we selected, for temperature, since we selected Schlumberger as the service, the automatically PLATO is looking for curves with the WTEP suffix, log name, I mean. Then for pressure, WPRE, gradient, FWETE, Warhol, TFHM. But for the CCL, apparently the CCLC is not working. So I click on the value and press assist, and I see that there is actually a CCL curve, but it is just called CCL. So to correctly map it, I select CCL here. Okay, okay, and evaluate. Okay, and then I will speed up a little bit. Since in PLATO you are going to compare theoretical data with a theoretical model with actual data, you need to have a process interval that is containing data that you can compare to. If this data here, you can see this spinner data, it's becoming straight lines. Also, the line speed is starting to deviate. So this is not data that you want to incorporate in your probabilistic approach. You want to limit the data data interval to data that is actually showing what's happening in the well and that you can use for the probabilistic purpose. Of course, before you start removing data and trimming the interval, you want to display the perforations. And we are going to display the perforations by using this wellinfo.par. So those are parameter files that you can import in PLATO that are presetting a number of parameters. And in this case, it will include the parameters, the perforations. So this what we generate for our customers or let them generate is the par files containing the perforations so that customers don't have to enter them manually. So this is an Excel macro that we provide to our customers. They can specify top and depth of each perforation, the well depth units, the path to where to save this file, and then generate it. So this is, of course, if you have 3 perforations, it's a bit like over. Everybody can manually enter 3 perforations. But if you have like 100 perforations or even 40, you really don't want to enter them manually. So then this Excel macro-enabled Excel file is very handy. But we will import the perforations using wellinfo.par. In V8, it's very easy you can use drag and drop to import those parameter files. In this version, we have to go to the data tab, then to parameters, and yes, browse to the correct location, wellinfo. And you can see that now the perforations are displayed. Okay, so I'll trim the process interval, making sure that I am not cutting away data that's across the producing interval. So I change my top process zone here by clicking here on the global editor, and here there's a zone to process. So I enter 2985 meters. That's where the data is becoming unreliable, down to 3270. Then I evaluate, and now you can see that you have an interval that is containing good data, and you are still including your perforated intervals. Then in pre-process, this is a subtask where you are filtering the data. So you select passes for processing, filter data, calculate error estimates, and you can calculate TVD and the geothermal for temperature analysis. So let's go to pre-process here and press this evaluate button. That's a button that is used in PLATO to start a calculation. So I press on evaluate, and then you can see a number of tracks appearing. In the first track, the caliper data has been used to calculate the pipe ID. So you can see decaliper. If I right click here on decaliper, I can change its appearance. I can make it a thicker line to make it stand out more. You can see that for temperature, a filtered curve has been calculated, a black curve. And also a temperature gradient. The pink line here has been calculated. For the pressure, a filtered curve and the pressure gradient has been calculated. And a filtered curve for gradient, water holdup, and the spinner data has also been filtered here. And the pipe inclination here was used to calculate a continuous inclination curve. So what you can do here is you can change the curve that you use for temperature, for example. You can take an average. For temperature, it's the rule of thumb to take the slowest down pass because that's the pass that is most representative of the temperature changes across the wellbore, because you don't have the hysteresis effect and the tool is moving slow, so you're not smearing out your temperature response. So for temperature, we typically don't average, but for other curves like pressure, you can take an average, and an average is done, taking an average is done from the screen. You select the curves you want to average over. We had 6 passes here. For gradient, you can also take an average. For the water holdup, it is a little bit more difficult because you see that some data is failing. You have this null data, well, not null data, but this weird behavior. So we are not going to select those passes. And if we compare the water holdup to the gradient, it looks like the water holdup, it is showing a higher water content or a different fluid contact between hydrocarbon and water than the gradient data. Then let me hide some tracks here. So the pressure gradient is more in agreement with the gradient. It's showing the contact is here, but the water holdup data is, the curve selected is showing the contact here. So I will make sure that I select a pass that is showing the contact here and not the contact there. Therefore, I right click in the track, I uncheck pass number 1, and then I look for a good pass, and I take the dark orange pass. So I select pass number 4 and recalculate the curve. And now it's the fluid level is at a better depth, but we have this weird behavior. So what I can do here to avoid this weird behavior is to select the one pass that is going all the way down to the bottom. So I right click there, uncheck pass number 4, check pass number 6, snap to bottom zone, evaluate. So you can see that you can select passes, different passes in different zones for this filtering process. Then we can already continue to the next subtask. We did some averaging, we filtered curves, We made some modifications. I calculated the pipe ID from the caliper data. Next subtask is the spinner calibration. So spinner calibration. And as we mentioned before, in PLATO, the spinner calibration is done by comparing theoretical spinner curves to the measured spinner curves that are, the theoretical spinner curves are generated from the slope, threshold, and the apparent velocity. I will quickly show this. So if you press global optimization, PLATO will generate in the spinner track additional curves called spinner eval. If I hide spinner filter, toggle between spinner filter and spinner eval, you can see that the match is pretty good. So the theoretical and the measured passes are nicely overlapping. But something that you observe here is that the blue curve, I can highlight the blue curve. This is curve, blue curve is curve 7. Yes. No, pass 2. If I put the cursor on the curve, it's pass 2. You can see it in the value bar. At this depth, it's suddenly getting a value, an RPS value that it's negative and higher than the next two passes. So the curve should behave like tram lines. They should not intersect. They should not cross each other. But here, the blue curve, it is crossing with other data. And if we look at the spinner X-plot, that's spinner X-plot first rescale, you can see the linear match between the measured and the theoretical spinner data. And also here, this is this plot where we are showing the RPS versus relative speed between the fluid and the cable. So this is in fact the static response. And in order to have a very good spinner calibration, all the data should fall on a straight line. And here you can see most data is falling on a straight line, except for this blue data. So we have a number of options to remove this. We can either draw a box around this bad data. So here I can draw a box around this bad data. Save this. And then the bad data in this box will not be used. Or I go here and I use my quality flag parameter to remove the blue paths in the section where it's not reliable. So for example, here is the depth where the blue curve is starting to merge with other passes. So drag the cursor up until where it's making sense again. So the blue curve is once again at its expected position. So then I select edit spinner Q flag. I can uncheck pass number 2. Then I only want this zonation to this curve to be deselected in the zone that I manually specified. So freehand zoning. Okay, and then if I do a global optimization, it's no longer going to use the blue curve. So this functionality allows to remove bad spinner data so that in the end you end up with slope and threshold and an apparent velocity that is in agreement with all of your data. Okay, so I'm getting very short in time now. So profile, so spinner calibration is finished. We have a reliable apparent velocity. Go to the profile subtask, rescale, and in the process subtask, the analyst is going to define which zones are potential production zones. And you can do that using the temperature gradient. You can see the clear spikes here. The temperature itself, absolute temperature, and the apparent velocity that is showing increases where production is occurring. So I can make it a very simple model. So first fluid entry is shown by the temperature here. So I mark this first step as a production zone. Then everything above it is flow. And then, yes, let me make it a simple profile. So produce, and here you can see a little bit of frictional heating, temperature spike, and the velocity is also showing a change. So let's make a different zone here. And what I in fact doing is I'm breaking up the well in potential production zones. And these different production zones are zones where PLATO can calculate a different production rate. So in every zone that I'm labeling here, PLATO will be able to calculate a different production rate. If I select just one big zone, like here, then PLATO can calculate only one rate. But by taking account of the changes you can see on the velocity and the temperature gradient, you can specify zones in such a way that PLATO can calculate different production rates. Okay, so let's start with this. It's going to be enough for this case. So all those zones are zones where the velocity is changing. Actually, I made a mistake here. Still production here. So I go to the global editor, and because I have to enter some PVT information. And PVT information, I never enter surface rates because I want to see what PLATO calculates without imposing surface rates. So the salinity was 250 in this case. The oil API, it is 31.9, and for specific gas gravity, I don't have information. I'm not going to enter any sour gas compositions or BO values, so I'll just start with this. Just the oil API and water salinity. Then I press evaluate to register these potential production zones and do some pre-calculation of PVT properties. Then I go to the process subtask where the optimization is occurring. So it's going to occur. So global optimization, click here. You can see after the global optimization, the production profile has been optimized. You can observe a good match between your theoretical and your measured curves for all of the data. But what you notice is that the curves suddenly have become more blocky. That's because a sampling reduction has been done to make the optimization go faster. In a case like this, it won't make that much difference to do the optimization with all the samples, but in many of the cases that we're working with all these many perforations and complex situations, then it's really helpful to reduce the amount of samples or measurements used in the optimization and gradually increase the amount of measurements that you are using in the optimization until you can use all the measurements. So this is done in the sampling level. You can see automatically PLATO selected level 5, but you can also go to level 10. Then you are going to optimize the production profile using more data. You can see the curves are becoming more continuous. Eventually, you use all samples. And eventually, if all samples are used, you can go to the final subtask, evaluate, and now you have your downhole flow rate and your gas and oil rate at surface conditions. So this is oil, but of course there is gas in solution. So this is the solution gas that's been calculated, and that's the rates you get at surface. So for water, there is a ridiculous amount calculated. If you enter any reasonable scales, you will not see water anymore. So this is a very quick analysis. If I was a bit faster with my first explanations, I could have shown that you could also add the temperature here. Temperature can be added, and you can also import the stations to have these local spinner constraints that are working and showing an agreement between the model and the theory. Okay, and finally, if this has been done, you can generate a report in the Word format for all the types of measurements that we can analyze in PLATO. So for all the conventional tools, of course, at the DTS, and for array tools, for each type of array tool, we have a different model template, report template. Okay, so I'm afraid that I went a bit over time.
I believe you are in time. Okay, perfectly. Okay, so it's less than 90 minutes. Okay, I'd like to thank you. It was really informative webinar. And if you have access to the chat box, some people sent some questions. You can see them.
I will check, yes.
I have a question.
Yes, you can jump in, Virginia.
Can I ask? Right.
Yeah, for sure.
Thank you very much, Alain. It was really very good presentation and overview of everything you can do with ISP software, but also maybe you answer this question. Sorry if I, but can you? You said you could integrate production logging with DAS and DTS, and you also explain for the production logging interpretation, you can integrate, the importance of use temperature in the model along with a spinner. Is it possible that you also integrate acoustic data from noise or acoustic sensor like hydrophones? Is that something that you have done with PLATO?
So currently we can visualize this noise data, but we are not doing any processing. So we can use it qualitatively.
Yeah, very good. And is there a plan that you think you would like to do that?
Yes, we want to do that. Yes.
Yeah, thank you.
Okay. You can see the chat box.
Yes, there is Mahmoud Sada that asked a number of questions.
This is the criteria.
Okay.
What is FBE? FBE.
That is a frequency band energy. So let's if I can some backup slides too. So you have DAS data in different frequency bands, and this
the question about DAS. Okay.
Yes, so you have FBE is frequency band energy, and this is the energy for the frequency band from 5 to 10 hertz. This is from 10 to 15 hertz, and here you can nicely see fluid moving up on the color maps. The FBE, that's the FBE.
Okay, you can go to the next question. Okay, no problem.
Okay, so for the detection, automatic detection of production zones. Yes, so it's this is controlled using equation number dialogues like you can see here. You can pretty much like when you select passes for spinner passes or production logging passes, you can specify which bands you want to use. Here there are 3 three FBE bands, 0 to 10 Hertz, 10 to 15, 15 to 20 Hertz. And for each of them, the total DAS energy over this time interval having calculated. And then as a user, you select which ones you are using. And then you can specify thresholds to determine starting from which total DAS energy you label a zone as potential production zone or not. There are, of course, default values in PLATO that you can keep if you are comfortable with them. But a tip, we also work with statistics so that a production zone is a zone is labeled as production zone if, for example, the value is 95% higher than all the other spikes, all other data, or as a second threshold for the zones with less production, 75%, lower than 75%. And then that's just what you see here. So you have zones with a higher production rate and zones with a lower. And then eventually you can, in this subtask, you can decide DAS intensity, whether you want to use it, completion information, so that you are only labeling zones that are perforated, or temperature gradient. So that's completely up to the analyst, and you can make it exclusive or combined. So it can be that you impose the condition it has to be perforated, DAS energy has to be high, and the temperature gradient has to be high before a zone is labeled as production zone. Or you can make it just any, if it's on any source, then label it as production. So that's up to the analyst.
Okay, I don't see more question. Okay. Dr. Mohammed have been add a link for our LinkedIn page. It will be if you like to follow our events or activities. Okay, it will be a good choice to connect there. There is a question about DAS temperature modeling. What's DAS modeling?
This is my question. I'm sorry.
Yeah, you can, Arthur, you can jump in. Yes.
Yes. Good evening, everyone. I have a question. Maybe it's not related directly to this, our production logging, but I think it's related to the production profiling. This is the DTS. By the way, the question about the temperature modeling. Are the plot, available to use the DTS for the temperature modeling, and the temperature modeling can be applying only for borehole profiling, or we can be using it for behind casing profiling as well? This is my question.
Yes, behind casing, to a limit, we are not modeling what's happening in the reservoir. So it's more like axial model. We can change the position of the fiber. We can specify that the DTS fiber is behind casing, but we are not modeling the temperature behavior in the reservoir, except for the warm-back model. But in general, we don't. It may come.
Warm-back, you mean the transient profiling? When we use the several temperature, like a warm-back, and we can apply this for temperature modeling?
Yes. So for the warm-back, it is a reservoir model. So for the warm-back, we can calculate injection profile, and also like the fracture growth can be estimated from warm-back data. But otherwise for casing leaks or so,
are you applying this warm-back with injection or production profile simultaneously, or just because this is this transit, it is something like between the production and injection, or in between the static, and what exactly this profile are showing in this case?
So we analyze them separately. So the warm-back first, and then the profiling, the production. But for production, then we do some optimization for the geothermal.
Mhm. Okay, it will be separately. I mean,
For
Okay.
now, yes.
Mhm. Okay, thank you very much. Thank you for presentation and thank you for your questions. Thanks, guys.
So if anybody have any question, it can jump in. I will have like I'll ask few questions, okay, for the benefit for anyone. So Alan, if somebody want to enhance its experience in this software, it can ask ISP for a demo license. Like, and how many days this demo will work? Like 1 month or something?
Yes, we have different formulas. We can currently we are using different licensing programs, so we can provide licenses for any time that's agreed between us and the potential tester. So we can extend the testing, and also we can help with doing a demo before they start testing, because with PLATO there is a lot of not
Okay.
always super easy. So
Okay. So there is a possibility if somebody want to enhance its experience to get a demo, okay, this will be great. And if somebody also want to get materials like examples, I know it's come with an installer, or it's you can send them by email, like basic and advanced example.
Yes, we have different tutorials, and for each tutorial there is a data set that's released that we can use for training purposes.
And can be shared with the people
Yes.
enthusiastic to like to learn PLATO. Okay. I don't believe there is more question. Okay, I believe we'll conclude our lecture. So I like to thank you so much for your volunteering time and to spread the knowledge. Okay, free knowledge. Okay. I like to thank our attendees to attend these lectures. It was really informative time. I hope everybody get benefited from it. Any last word, Dr. Mohammed? Dr. Mohammed, I believe.
Yes, Mr. Mazen, can you hear me?
Yeah, now I can hear you.
Okay, that's great. Mr. Alain Gysen, thank you too much for your insightful presentation and joining us today. I mean to SPWLA Iraq chapter. Thank you for everyone who joined us too today, and hope to see you again in another webinars in the future. Bye-bye.
Thank you, Doctor. Thank you, Alan, and thanks for our attendees. Hopefully, we'll see you on the upcoming webinars. Thank you.
Thank you very much.
Thank you
Thank you
very
for
much.
the invitation.
Thank you.
Thank you
Thank
for
you,
Thank you,
inviting me.
Alan.
and
Bye.
Dr.
Have a great day, everyone.
Thank you.
Bye-bye.
Thank you. Bye-bye.
Bye-bye.
Thank you. Bye.
Thank you. Bye.